Log on, tune in, find out. Another good idea from Cambridge.
So it's now for David Vogan to do the last round of his series of talks.
Thank you.
So what I'd like to do today is give some sort of outline of how to compute, well, how to find unitary representations among these irreducible GK modules. So I recall that I had this G, which was complex algebraic, equipped with, I forget what I called it exactly, fixing a Borel subgroup and a maximal torus and a pinning. And delta 0 was supposed to be an automorphism of order 2 of G, preserving this box. And so I made this little group gamma, and G gamma was the semi-direct product of G and gamma, and I had an element X in the non-identity coset with the property that X squared is in the center, so that's what I want to fix, and then K was by definition the centralizer in G of X. So this was the complexification of the maximal compact of some real form G of R, which is otherwise invisible. And what the Valence and Bernstein theorem that I mentioned last time says that irreducible GK modules with trivial infinitesimal character so this is the easiest case, but it's the one I'm going to do. So these were in one-to-one correspondence with irreducible K equivariant local systems on orbits of K on B, the variety of Borel subgroups. And even, well, more is true. So you may be, well, I'll do it over here. You may know very well that in category O, any irreducible L of lambda is the canonical quotient of a Verma module m of lambda, and these things have a much simpler character theory than the L of lambdas, and what happens is that if you take the Grothendieck group of O, then of course this is a free Z module with basis these various L of lambdas, but it's also useful to know that it's a free Z module with basis this set of m of lambdas, and the original, in a sense, the original subject of Kazhdan-Lustig theory was finding the change of basis matrix. So I want to say that all of these very easy things have an analog over here. So well, let me write just in order to keep the analogy, lambda is going to mean some irreducible k-equivariant local system on an orbit. One of these things here, and I'll write L of lambda for this corresponding irreducible GK module. And then all of these statements have analogs. So what happens is that L of lambda is the canonical, unique, irreducible quotient of some what's called a standard GK module. M of lambda, and these things are in some way, well, these are less complicated. You can't say they're simpler, but they're less complicated than L of lambda. Just as with the Verma modules over here, and all of the other words are the same. So the same things that I said for category O, and in particular, there's a Kazhdan-Lustig theory for the change of basis matrix. Between these M of lambdas and L of lambdas. So if I, well, I could say, I don't know, P mu lambda, this is some polynomial in Q, and the coefficients correspond to the multiplicity of this local system mu in the perverse extension of and I should say in the cohomology sheaves. Yeah, the power of Q has to do with the degree in cohomology. I won't get it straight, but so these are, as Cedric has mentioned, this is why these coefficients are non-negative integers, and then the statement is that let's see, I think I'll get it. Well, let's see. It's the sum over mu. There's some power here, which I'll explain. And I think I may have this right. So here, this mu is the dimension of the k orbit that's underneath mu. So I may have this completely backwards, but something along these lines is true. This is in a sense just a completion of what I was saying yesterday, and what in fact, a little bit, a tiny bit in the spirit of some of the things that Raphael was saying at the end. What happens is there's an algorithm to compute these polynomials, and what it's based on is you have so for each simple root s, there's a P1 fibration like this, call that pi s, and what the algorithm essentially uses the decomposition theorem for this map, for these various maps, pi s, and so because these are P1 fibrations, everything that's going on, all the geometry is geometry inside P1. It's very, very easy to compute, and the decomposition theorem tells you that perverse sheaves have to behave in a certain way under these maps, and putting those things together, you can get an algorithm to compute these things. So that's all old mathematics. What I said I wanted to do was talk about how you find unitary representation. So what can you say about unitary representation? So so the first thing well, so I have some GK module. Am I allowed to call it? No, maybe it better be V. And what I want to know is whether V admits an invariant Hermitian form. Well, the first question is whether V admits an invariant Hermitian form. And the second thing I want to know is whether the form is definite. That's what you have to decide in order to find unitary representations. So this first question was answered by Knapp long ago. Maybe it's a Knapp-Zuckerman paper, sorry. And in this context, their answer can be phrased like this. Well, so I want. Well, let's see. So the point is. Yeah, the point is that you can define a new GK module. So this V sub h, these are k-finite linear maps from V to C, but I want to endow them with the opposite complex structure. So I that makes perfectly good sense. I just replace multiplication by z with multiplication by z bar, and this makes good sense. And what's very easy is that VH is another irreducible GK module. And so what's also easy is that V admits an invariant Hermitian form. If and only if VH is isomorphic to V. So a sesquilinear pairing on an invariant sesquilinear pairing on V is the same thing as an isomorphism. from, sorry, it's a GK morphism. So that's makes everything fairly simple, and so the the question is what's this map V goes to VH in the Valence and Bernstein classification? Sorry? Yes, sorry, yeah. Yes. Yeah. Yeah. Sorry, I should say non-zero. I mean, non-zero is the same as non-degenerate for an irreducible module. So in order to tell which modules have Hermitian forms, we just have to figure out what this involution is on irreducible representations. And that's not very hard. What happens is, remember, I constructed this group K using an element X. So X acts on the category of GK modules. What you do is you twist the action of G by X, and you don't change the action of K. So I can write this as V goes to V twisted by X. And the proposition, which I think this is basically Jeff Adams, is that this is the isomorphism that we're talking about. That this Hermitian dual operation is just twisting GK modules by X. Okay. So, well, and the nature of the proof is that this map was computed by Knapp-Zuckerman. This was in the pre-Valence and Bernstein days, when you had to know what a discrete series was and things like that. So it's a question of translating their computation into this language. Okay. So now what I want to do I want to enlarge I'm not sure. This notation is a little peculiar, but just the group generated by K and X. I mean, these commute. This is a very boring kind of extension, but there it is. And what, well, I mean, it's an extension like this, and so sort of Clifford theory tells you that, well, it tells you, for example, that an irreducible representation of K gamma is either an extension of an irreducible representation of K that's fixed by X, and in this case there are two possible ones. Or it's induced from K to K gamma of an irreducible of K that's not fixed by X. So that's easy stuff. And the same thing applies to these perverse sheaves and so on. So what happens? What I want to say is that this theory of GK modules with invariant Hermitian forms, well, I'll just be a little fast and loose, is tied up with these K gamma equivariant perverse sheaves on B. That's the statement that I want to make. So in particular, what's among these irreducible GK modules are those with an invariant Hermitian form, and that corresponds over here to the K equivariant local systems that extend to K gamma equivariant. And necessarily they extend in two ways. And the nice thing about this too is that there are always two equivalence classes of invariant Hermitian form. Well, whatever invariant Hermitian form you choose, you can choose also its negative. And I'm claiming that those two choices correspond to these two extensions of an equivariant local system. Okay, so the story So the next thing that you have to do is extend the Kazhdan-Lustig algorithm to compute these perverse extensions of these k gamma of these k gamma equivariant local systems. And this is this is I mean, I haven't managed to do it, but it's pretty easy. I actually at some point I had a partial algorithm, and I know just enough about computer programming to be dangerous, and so I took Foucault-Ducloux's beautiful Atlas software and I modified it to compute the Kazhdan-Lustig polynomials in this setting in a special case, and of course right away got these answers of 4 billion. You know, I got negative coefficients right away, but eventually figured out how to fix it, and so I think that this is possible, and what emerges is, well, you can, in some explicit computable way, write an invariant Hermitian form on an irreducible GK module, if it exists, as some sort of integer combination, like the formula that's written up here, of invariant Hermitian forms on standard modules. So what does that mean? So everywhere should be some non-degenerate, and this should look terrible to you. Fortunately, I erased the Verma module example. This should look terrible to you because what you learn in the basic theory of Verma modules is that you can't put a non-degenerate invariant form on an interesting Verma module. In the setting of Verma modules, if you make the Shapovalov form or something, the radical of the form has to be big. Well, there's no. So how can you talk about non-degenerate forms? So let me try to explain that. Well, first let me try to explain it for Verma modules. So I have this L of lambda what shall I call it? I don't know. Well, I know what I'll call it. I'll call it M1 of lambda. Maybe that's a good idea. So what happens? So what Shapovalov does, he puts an invariant bilinear form on this M of lambda. Now, M of lambda, this Verma module, you can think of as the enveloping algebra of some opposite n minus. So this is on some constant vector space. So this is a family of forms on this U of n minus, and they make the weight spaces of U of n minus orthogonal to each other. And those weight spaces are finite dimensional. And on each weight space, you're talking about a bilinear form on a finite dimensional vector space, so it's some symmetric matrix, and it's what happens is that symmetric matrix depends in a polynomial way on this highest weight lambda. Okay. Well, the form on the zero weight space is non-trivial. This form is never zero. But what happens? What happens is that this M1 of lambda is exactly the radical of the form of this Shapovalov form. And so in particular, if L of lambda is not the same as M of lambda, then the form is degenerate. So what do you do? Well, Janssen long ago told us what to do. He said, he defined, well, a natural filtration of M of lambda, which you can think of as essentially the order of vanishing. The definition is slightly tricky, but not very. It's the order of vanishing of the Shapovalov form. So the picture is This is m of lambda, and it has m1 of lambda. That's what I wrote up there. But then m2 of lambda, m3 of lambda, and it's a finite filtration because, more or less, because these are polynomials. Well, eventually you get 0. And what he showed was sort of taking residues. You get a natural non-degenerate form. Let me call it the ith form. This is on mi of lambda modulo mi plus 1 of lambda. So this is old, wonderful mathematics, but long time ago. So what happens is, so what I want to say is that you should in some appropriate Grothendieck group, you think of this Verma module as identified with the associated graded thing, the sum from I equals 0 to m n minus 1 of these mi over I plus 1, whatever I wrote. And this is now endowed with this form. And this is non-degenerate. So the Verma module doesn't have a non-degenerate form, but in the Grothendieck group, there is a natural non-degenerate form. So it's the same thing for Harishchandra modules. I won't, let's see. Where shall I? Okay, so what happens in the world of Harishchandra modules? So what was very important for this Janssen construction was the key to this was deformation of lambda. In order to define this, well, when you say order of vanishing, that's something you can only say for a function of one variable. This lambda depends on several variables, and you should probably use deform in the direction of half the sum of the positive roots or something like that. but it's certainly important to have a continuous deformation in order to be able to talk about this. And in the world that I'm talking about, there don't appear to be any continuous parameters. The parameter set for these representations that I've described is a finite set. And so there's a problem. But what happens so well, I'll just say that it turns out that well, any standard Harish-Chandra module, this m of lambda, appears canonically in a continuous family. So I don't think I can say anything useful about this, but so the continuous parameter is some variable in. So this is the -1 eigenspace of the Cartan involution on some theta stable Cartan subgroup subalgebra. And so I can write this parameter is that there's some discrete part and well, I don't know, nu of lambda. I'm not explaining this decently. At any rate, you get a continuous, you get a, well, you get a one parameter family, m of, well, I use the same discrete part and just scale this. That makes good sense. And what happens is that these these all have Hermitian Langland's quotients, irreducible quotients, and so there's a notion of Janssen filtration, therefore a non-degenerate form that I can write with a subscript t on some associated graded okay, so at any rate, one of the things that I've done is defined a non-degenerate Hermitian form on the standard module, at least in the Grothendieck group. Yes, that it has to, because yeah, I mean, this is more or less, this is among other things a character of a Cartan subalgebra, and so you're deforming the infinitesimal character, just as in the Janssen case. Okay, so at any rate, this makes sense of the statement which is up here, and so what I've done. So this defines some non-degenerate Hermitian form on each standard module in the Grothendieck group. And it writes a form on an irreducible as a computable combination of the forms on standards. Okay, so that's nice as far as it goes, but I was interested in the question of what's unitary, and this. What happens is that these forms on standard modules are peculiar. So let me give an example. In the case of SL2R, what's called the spherical principal series, representation. This is the sum of all the even characters of SO2. And there's some parameter bigger than or equal to 0. So what's the signature of this form look like? Well, it depends on T. If I can remember what the even integers are. So the form has all pluses for T between 0, for T strictly less than 1, then it becomes like this for 1 less than or equal to T less than 3. And then it becomes, the pluses continue. So this is for 3 less than or equal to T less than 5. It's, if you can make sense out of these pictures, it isn't hard to guess what the pattern is. But the point is that it's complicated. These things are kind of a mess, and so in order to detect unitary representations, you need to compute these signatures. These signatures for standard representations. You need to know what once you've written your irreducible in terms of standards, well, then you need to know how the signs looked on the standard characters. And that's, I have 3 minutes to do, so I'll tell you how to do that. Well, I'll tell you that Janssen did it. So what happens is that Janssen's theorem, I mean, you need to make sense out of these statements, but the signature of one of these forms is semi-continuous in T. I don't know from which side. You can tell from what's written here. What happens is the change in the signature from what? From T minus epsilon to T. I mean, it can happen, for example, at T equals 1, that there's a change when you go from 1 minus epsilon to 1. And this change is the sum of the signatures on the odd levels of the Janssen filtration. For T. Well, so at most values of T, the Janssen filtration, I mean, if the form is non-degenerate, the Janssen filtration is trivial. There's only M0. There aren't any odd levels. There's no change in the signature. But something interesting happens. And this is what I just got done saying was computed by this Kajdan-Lustig theory. So everything's computed, and I have a minute to spare. But I'll stop there. Thanks.
Are there questions, comments? Is this standard module corresponding to the principal series representation?
So that's the question is what you mean by principal series. It's the standard modules are induced from cuspidal parabolic subgroups by limits of discrete series representations. It certainly includes the principal series. I mean, sometimes principal series refers only to the minimal parabolic, but those are included, and these things are, well, what principal series should have been defined to be. So
if we consider the discrete series, so what's the image in the GK module?
The discrete series correspond to closed orbits on the flag variety, so the perverse extension of the local system is just trivial. The standard module is equal to its irreducible quotient, and the discrete series carries a natural Hermitian form, which by Harishchandra is positive definite.
So at the end of the day, do we have like a list of irreducible unitary representations?
No, this is a way to generate the list. And it hasn't been, you know, the I's haven't been dotted and the T's haven't been crossed. I really hope that we can put a lot of this in software in a matter of a few months, and then, well, I mean, for one group, for a fixed group, it's a finite problem. I mean, that's not obvious from what I've said, but it's supposed to be clear from what I've said that if you take a single irreducible representation, that this is a finite algorithm to decide whether it's unitary. And it's known that you only have to look at a finite number of cases, and then you can get a complete description.
I have a question. So about a year ago, there was some news making the round of the world about something in E8. So this means in this framework now, this
That was
completely carried out in E8.
No, that was calculating just the classical Cauchy-Moustic polynomials for the real group E8. So computing these perverse extensions for orbits, I mean, more or less spin 16 inside E8, looking at its orbits on the flag variety and local systems and computing those perverse extensions. So what actually, in order to carry out this algorithm, you need to do some jazzed up, slightly more complicated Cauchy-Moustic algorithm. But in the case when the Cartan involution is inner, this kx, this is essentially a product. There's nothing going on, and so the polynomials are just exactly the same as classical polynomials. So in this, if you want to do this unitarity stuff for E8, there are some harder calculations still to be done for smaller groups that appear inductively, but for E8, the Cauchy-Moustic polynomials that are known are what you would need.
Further questions? Then let's thank David not just for this talk, but for the whole series.